Hello everyone. Today I'll be talking about semantic search using BERT versus TF-IDF. This project dives into how search engines have evolved from simple keyword matching to understanding the actual meaning behind what we type. I'm Rishikesh and I'm from SRM University and I'll walk you through how these two methods, TF-IDF and BERT, work, how they're different, which one performs better in practice. For example, think about every time we search something on Google, it looks through billions of web pages, yet somehow the most relevant one appears right at the top. How does it know? Search engines basically have two ways of thinking. One is old school TF-IDF. It just for exact words. And then there's BERT, an AI that actually understands what we mean. It's like asking a friend, where can I buy a Jaguar? TF-IDF would think you're going to the zoo. Bert would say, oh, you mean the luxury car. So yeah, smart search versus dumb search. What is information retrieval? Before we go deeper, let's quickly talk about what information retrieval is. It's the science of searching for documents, information, or metadata with large collections. It's basically the science, like Google, YouTube, Netflix, and Amazon do. Even something small like searching for a message like mom on WhatsApp is nothing but form of IR. But the tricky part is humans don't always type perfectly. For example, when someone searches Apple keyboard is not working, IR has to figure out that you're talking about the brand Apple, not the fruit. So the hardest part in IR is understanding what people really mean, not just words they type. So these are the project objectives, understanding both methods, analyze semantic differences, evaluate performance. The goal of this project is pretty straightforward. We're going to understand how both TF-IDF and BERT work, compare how they retrieve information, and see which one performs better in real-world searches. If I had to sum it up in one line, TF-IDF is fast and BERT is smart. And by the end, you will see why the balance matters. TF-IDF, the mathematical foundation. TF-IDF, what is it? Alright, let's start with what is TF-IDF. It actually stands for term frequency, inverse document frequency. Sound fancy, right? But it's simple. TF tells us how often a word appears in a document, and IDF tells us how rare that word is across all the documents. Here's an easy example. Imagine you got 100 recipe books. The word recipe appears everywhere. Boring, right? But the word lasagna only pops in a few. That makes it special. So TF-IDF says, cool, let's give higher importance to rare meaning words like lasagna instead of overused one like recipe. These are the formulas we can use. Term frequency, inverse document frequency, combined term frequency, IDF score. TF-IDF processing pipeline. Behind the scenes, TF-IDF goes through a little assembly line. First, it takes the raw text, then splits into words. That's called as tokenization. Next, it turns those words into numbers. It's also called vectorization. Finally, it compares document using cosine similarity. Imagine, for example, imagine two documents. Document A contains car and price, and document B contains car but cost instead of price. If you and the query we search is car price, document A wins because it matches exactly. TF-IDF in action. A practical example. The query car price. We got four documents here. The car price is competitive, vehicle cost analysis report, automobile pricing trends, car features and specifications. These four sentences mean the same. The meaning is same. Uh, A sentence like the car price is competitive, it's a high score, but something like vehicle cost analysis report scores low, even both meaning the same thing. TF-IDF basically TF-IDF doesn't understand the car and the vehicle are synonyms or that cost and price are related. It's the same issue if you search doctor's salary. TF-IDF might totally skip an article title physician income because the keywords don't match. The coming to the limitations part. Limitations of TF-IDF. So yeah, TF-IDF has a big flaw. It only matches words, not meaning. It doesn't understand synonyms, sarcasm, or even basic context. It's like trying to have a deep conversation with a calculator. Funny, right? For example, if you search Apple stores near me, TF-IDF might show you a fruit shop instead of a app store. It's funny, but it shows how literally the system is. It can't help it. Measuring similarity cosine distance. Now about cosine similarity, that's just the math in TF-IDF uses to figure out how close two documents are. In this picture, every document has a narrow arrow in space. If two arrows point in the same direction, they're talking about the same topic. If they're apart, they're unrelated. You don't have to do any math here. Just think of it has checking how aligned two pieces of text are. Enter BERT, contextual understanding. Finally, BERT. BERT, what it stands for? It stands for bidirectional encoder representation from transformers, a model made by Google in 2018. What makes BERT amazing is that it reads sentences both ways, from left to right and right to left. So it actually understands the context. Take these two sentences for example. He went to the bank to deposit money. That's financial bank. The second sentence is he sat by the bank of the river. That it means that's the river bank. TF-IDF treats both as the same because it has read the words where it actually mean. BERT knows they're totally different. That's what it makes so powerful. Cinematic embeddings, the power of context. BERT works by turning words and sentences into dense vectors, basically group of numbers that capture meaning. So if you search on YouTube how to remove pimples fast, BERT doesn't just look for the word pimple. It also finds videos like how to clear your skin naturally or get rid of face spots because it understands the meaning, not just the words. That's semantic search in action. It knows what you're trying to say. Sparse versus dense vectors. Here's the difference. TF-IDF creates sparse vectors like checklists with mostly zeros and ones, and BERT creates dense vectors, means every single number carries a bit of meaning. So TF-IDF like a list that just says whether a word exists or not, while BERT is like a brain that stores those words and their meaning. Simply sparse vector is equal to shallow understanding and dense vectors are equal to deep comprehensions. Mathematical concept behind similarity in BERT. BERT also use cosine similarity just like TF-IDF, but now the vectors actually hold meaning. So we are comparing ideas, not just words. So if I search a sentence, car broke down, repair cost. TF-IDF might miss it completely, but BERT would show pages like vehicle engine repair charges or auto repair expenses, even though not a single word matches the meaning. Yes. This is the comparative graph. TF-IDF versus BERT similarity. You can see the differences of car price versus vehicle and the word meaning differences. Uh, Coming to real world query comparison table. Real world query comparison table, let's look at some real world examples. For example, search the sentence how to treat cold. TF-IDF might bring up cold storage tips for vegetables. Bert knows you're talking about being sick and shows home remedies for flu. Or try sentence cost of vehicle. TF-IDF misses car evaluation guide. And BERT instantly connects car is equal to vehicle and cost is equal to price. And that's why today's search engines feel so intelligent. They understand our intent, what actually what we mean. TF-IDF versus BERT, the trade-offs. uh, TF-IDF and BERT differences. Now it's all perfect. There's always a trade-off. TF-IDF is super fast, lightweight, and simple to implement. It's great for basic keyword searches or things like autocomplete. BERT, on the other hand, is slower and needs more memory, but it's incredibly accurate because it's understanding meaning and context. In real life, many systems combine both. They use TF-IDF for quick filtering and BERT for deeper and smarter results. So speed versus accuracy. This is evolution of search. Let's quickly look at how search has evolved. Back in the 1980s, it was all about exact keywords, ints and ors. Then came TF-IDF and PageRank in 2000s. Making such more relevant in 2010s. Machine learning and word embeddings taught system basic meaning. And then in 2018, BERT arrived, truly understanding context. Now we have massive transformers models like GPT that can actually talk to us, generate text, and give conversational answers. Remember how old Google is used to be. Uh, Google used to ask, "Did you mean?" like a question. Now it just knows everything. So to wrap up, TF-IDF finds document with the same words while BERT finds document with the same meaning. Semantic search is the future of information retrieval. Search engines today don't just fetch data; they actually understand us. Cool, right? Thanks. Thank you so much for watching.